So we will continue with chapter 12. For a short time, the path of the plane in the figure is described by y equals to 0.001 x squared in meter. If the plane is rising with a constant velocity of 10 meters per second, determine the magnitudes of the velocity and acceleration of the plane when it is at y equals to 100 meters. So in this motion, they gave us just the equation of y function of x, and we want to find the velocity and acceleration magnitudes when the plane is at y equal 100 meters. So this is the first information. The second important information is that the plane is rising with a constant velocity of 10 meters per second. Here they mean rising in y, okay? So in vertical direction, the velocity is constant. So what I can understand from this sentence is that Vy is equal to 10, equal to a constant, and I have y as a function of x. In order to get my velocity, I need to know two components. Vy is already known. I still need to find Vx, okay? Now, in order to find Vx, what should I do? What do you think I can do here? Let me try to think first. Can I write dx over dt? I don't have x function of time, so it will not work here, dx over dt. But what I have is y is a function of x, and I know Vy. And using the chain rule we introduced last time, we can benefit from knowing Vy by writing that Vy can be decomposed into Vy is dy by dt, okay? I can decompose it using the chain rule too by writing it as Vy equals to dy over dx times dx over dt. In this way, I can appear the term of my interest, which is dx by dt, since dx by dt represents Vx. Since I know Vy is equal, so here it's dy over dx times dx over dt. Vy is known, it's 10, so I can just replace it by its value. And I can derive y with respect to x because I have the function. So all I have to do now is to replace dy by dx by the derivative of this function, which is 0.002x. In this way, I am calculating what is dx over dt. So let us see in details the steps. So first I say, knowing Vy is equal to 10, and it represents y dot, which can be decomposed using the chain rule into dy by dx times dx by dt. dy by dx is 0.002x, and dx by dt is Vx. So now I can deduce the value of Vx for any position x. In particular, when y equal to 100 meters, if I replace in my equation of y, which is 0.001 x squared, I can calculate the corresponding value of x. And once I know what is x, I replace it back here in the formula. So replacing back x in the formula, I can get the value of Vx. Now, to get the magnitude, all I have to do is radical Vx squared plus Vy squared. The next step is to do the same procedure for acceleration. So first, I know that A is divided here into AX and AY. Concerning AX, I don't know it. I will try to find it. Concerning AY, I can easily find it because Vy is constant. Since Vy constant, 10, then AY is equal to 0. So I still just need to determine what is AX. Now I will follow the same methodology as I did for Vx. I will do it for AX. Because already here, I have the relation, so 0.002x Vx is equal to 0, which is the derivative of a constant 10. This equation, if I derive it with respect to time, then ax will appear. Why? Because this function, so I can simplify it to x vx equals to 0, because this is a constant. So if I derive, I can say that I should derive this relation. I have that x times vx is equal to 0. Okay. So if I derive this relation with respect to time, so d by dt, I have here the product of two functions. It's like u times v, and you know in derivation, if you have uv, it's u prime v plus v prime u. If I derive this relation with respect to time, I will get x dot vx, and you know what is x dot by definition? X dot is vx, so it's vx squared if you want, plus x times the derivative of vx with respect to time is ax. This is equal to 0. So by deriving this relation with respect to time, I was able to get my acceleration ax. Okay. So now we see it in stats. So for ay, it is 0 since vy is constant. Now if I derive the relation I had previously, I will get as we did together. So this is equal to 0. So the constant will be eliminated since it's equal to 0. And you will get vx squared plus xax equals to 0. And now already for any value of x, you can compute vx from the previous step. So now all you have to do is to replace back and get the value of ax. And since ay is 0, then the acceleration magnitude is equal to the magnitude of ax. Any question for this problem? Okay, so let us continue. Now, this part, I think it is the easiest part for you. It's motion of projectile. You have already seen projectile motion in school. So the projectile motion is particularly characterized by a constant vertical acceleration equals in magnitude to g, which is 9.81. So we can apply for it in y direction the formulas of constant acceleration, while in x, no acceleration. So ax is equal to 0. Therefore, in x direction, I can apply the rules of constant velocity, because acceleration is 0 means that vx is constant. So as a reminder of the main formula you can use in projectile motion, first, as we said, in x direction, ax is 0. So I can apply, if I put a equal to 0 in my equation developed for constant a, I can deduce that vx will maintain a constant value, which is v0x. The position x is given by x0 plus v0 xt. And if I apply the relation independent of time, again, I will get that vx is constant. So this is for the horizontal motion and projectile motion. Now concerning vertical motion, all I have to do to derive relations is to replace a by minus g in the formulas of constant acceleration. So I get that vy is v0y minus gt, and y is y0 plus v0 yt minus half gt squared. Now concerning the relation independent of time, so here just we have a small typing error. So this is vy squared. So vy squared is equal to v0y squared minus 2g delta y. Okay. Let us do some practice problems on projectile motion. A sack slides off the ramp with a horizontal velocity of 12 meters per second. If the height of the ramp is 6 meters from the floor, determine the time needed for the sack to strike the floor and the range r where the sacks begin to pile up. So here in this problem, always in projectile motion, try to see what are your inputs to decide which equation to use. Okay? So the range by definition is x final minus x initial. This is the range in projectile motion. So the range is unknown. I want to find it. plus I want to find what is the time needed to reach B. Okay, so these are my unknowns. Now what do I know? First, I know completely the initial velocity. For the initial velocity, no y component, so I can write that v0y is equal to 0, while the x component is equal to 12, so v0x is plus 12. Now, the other information I know is that y initial, so y0 is equal to 0, because I'm starting from the origin A, and y final is equal to minus 6, because I know this height. So y final equals to minus 6. Since I know delta y, y initial, and y final, okay, then in order to get the time needed to reach B, the best way will be to write the relation of y. So I know that for projectile motion, y can be written as y0 plus, which is 0, plus v0yt, which is also 0 since v0y is 0. So this will simplify. Minus g t squared over 2. So knowing that at point B, if I apply at point B, y of B will be equal to minus gtb squared over 2. So replacing yb by minus 6, then I can get the value of tb. So this is first how I get the time needed to reach the floor. Now for the range, which equation I will use to determine the range? Look, I go back to the definition. What is the range? The range is x final minus x initial. Okay? X initial, I know it. It is equal to 0. It's x at A, so x initial is 0. So the range will be equal to x final. And x final can be simply calculated as x final equals to the equation of position in x is v0xt plus x0, but x0 is 0. So it's v0x times t. And since x final is at point B, so I should multiply by tb. tb is calculated from the previous step. v0x is 12. I replace v0x by 12 meters per second. So I can get the value of the range. Okay? Any question on this? Okay. So let us do another problem. The chipping machine is designed to eject wood at chips V0 equal to 7.5 meter per second. If the tube is oriented at 30 degrees from the horizontal, determine how high h the chips strike the pile if they land on the pile 6 meters from the tube. So, I have here first that the initial velocity here is inclined. So, and I know the angle of ejection. So I can divide the velocity into two components, one along x, one along y. So I can write that v0x is equal to 7.5 cosine 30, while v0y is equal to 7.5 sine 30. Okay, so I know x and y, initial x and y component for the velocity. I know also here the range. The difference between x initial and x final is given. It's 6 meters. I want to determine the maximum, the height h, where the pile will strike the floor. So here, I want to determine what is the height at this level. This is the question. Okay. So now, in this problem, I will start always from what I know. So I know the range. This will allow me to calculate the time needed to reach A, because I know the range and I know V0x. And I know that the range can be written as, which is x final minus x0. The range is simply V0x times t. So since V0x is known, 7.5 cosine 30, and the range is equal to 6, so I can find t. So we find t at point A. So this is the first step. Now, once I find the time at point A, now in order to determine the height h, I need to calculate y of A, okay? So now all I have to do is to write that y of A is equal to y0, which is 0 here because we start from the origin, plus v0yt. So here v0y is known, I replace it by 7.5 sine 30, minus g. In general, use g10, okay? It's easier for calculation. So let's say minus g over 2, so it's minus 5t squared. Okay, so in this equation, the only unknown will be t at A, because I know v0y and y0 is 0, so I can simplify y0. I can replace v0y by 7.5 sine 30, and I have minus 5ta squared equals to y of A. Here already y of A is the only unknown, because 2a we got it from the previous step. So we can replace ta by its value, then we get the value of ya. But just pay attention here, this is not the question. It's not, the question was not to get ya, it's to get h. If I do a simple analysis, if I look at my figure, I expect that ya will be negative. And I know that the distance from the floor is 2.1. So I can say that 2.1 plus h, which is a negative value, plus ya, which is negative, will give me the value of h, because h is the difference between 2.1 and this distance. And this distance is the absolute value of ya, okay? This is why, since ya is negative, I put here plus ya, since h is smaller than 2.1. So this will allow me to calculate the height at A, okay? Any question for this problem? Another problem. The track for this racing event was designed so that the riders jump off the slope at 30 degrees from a height of 1 meter. During the race, it was observed that the rider remained in mid-air for 1.5 seconds. Determine the speed at which he was traveling off the slope, the horizontal distance he traveled before striking the ground, and the maximum height he attains, and neglect the size of the bike and ride. So in this problem, also it's a projectile motion. This is the information we know. We have a rider going over a projectile motion. Now we know the angle of incline, 30 degrees, but we don't know the magnitude of initial velocity. So here V0 is unknown. And the second information we know is that the total time, so T at B is known. The total time of motion, TB, is 1.5, I think. Let me make sure. Yes, the total time is 1.5 seconds. So TB is equal to 1.5. This is all what I know. No, I know also in additional information that the difference between, so I know YA is 0, and I know that Y of B is minus 1. So the majority of information are about Y coordinates. This is why the first thing to start with is the equation along Y. Okay, so I will start by writing that YB is equal to YA plus VAYTB plus half A which is minus g, so a is minus g t squared. Now, I know t, I know the time, and I know yb and ya, then the only unknown here will be the component of velocity in y. And this component will allow me to get v0, because I can write that va, that vy0 is equal to v0 sine 30. So once you get vy0 from the equation of y, you can replace in this equation to get the value of v0. Okay? And now, once you have v0, then you can get vx. So vx is constant, is equal to v0x, which is equal to v0 cosine 30. So now, all I have to do to calculate the range, I still need to calculate, so we have three unknowns here. We have first the velocity at A, we got it, it's v0. We have the range, and also I want the velocity at B. So for the range, it is vx equals to v0x equals to v0 cosine 30 times the time needed to reach B, which is given. So once I get, this is the velocity. Now to get the range, I will multiply Vx by the time. So the range is equal to V0 cosine 30, which is Vx, times Tb. So I got in this way the range. Now, concerning the velocity at B, who will tell me how to calculate the velocity at B here? What should I do? What should I do to get the velocity at B? Yalla, who will tell me? It is simple. Look, I have
Shouldn't we use the equation of free fall?
The equation of free fall will give you, look, the equation of free fall will give you x function of time, y function of time, or you can get y function of x. But if you know if you want to find the velocity magnitude, we'll divide it into two components, one along x, one along y. The x component is constant, and you already calculated it. So already we know the value of Vx. So just we still need to get Vy, okay? How to get Vy at point B? So to get Vy at point B, I should go back to the equation of Vy. What is the equation of Vy? Vy equals to minus gt.
V0 y minus gt.
Yes, exactly. So at point B, to get Vy at point B, it's minus gtb plus v0y, okay? And once I get the value of Vy at B, and already Vx is a constant, I do the radical to get the total velocity at B, okay? Any question on this? Fine. Okay. Now, what we will develop together is the equations for curvilinear motion, okay? So until now, we considered the work in rectangular components. Now we will introduce a new type of frames, which is the normal tangential components, and sometimes they are very helpful in solution of a problem. Normal tangential components vectors are variable. So when you want to draw the frame, it's not a fixed frame. It will vary in position with the particles. And how we define it? At any position, I determine the velocity. Ut, the tangential component, is the unit vector. So the unit vector of V represents Ut, which is, if you want, like ijk, okay? You have here Un, Ut, Ub. So Ut is the unit vector of V, and it represents the tangential direction. So this is Ut. It is driven by V. So as V will change, Ut will change with it. So this is the first axis of my frame will be along the velocity direction. Now concerning the second vector, vector Un. So for vector Un, it's always perpendicular to Ut and directed towards the center of curvature. What is the center of curvature? When you have a curved path, at any instant during motion, you are going over a certain arc of circle, okay? So at any position, you can say, I am moving on a certain circle. So you can define in this position what is called the radius of curvature, okay? And of course, you can see that the radius can be variable here. So at each position, so for example here, this is the center. I have a new radius. So I'm moving on a new circle, on a small arc of circle. And here, for example, in this part, the concavity is upward. This is why Un is upward. While here, for example, if you continue to this part, you have downward concavity. So your circle will be like this, then Un will be downward. Okay? So UNUT is defined as the instantaneous plane of motion during curvilinear motion. And UT is the unit vector of velocity, while UN is the vector perpendicular to UT in the plane of motion directed towards the center of curvature. This is the definition of UNUT frame. Now we can see here in this figure how the radius of curvature can vary during curvilinear motion. So as you can see, at each position, you consider that you are moving on an arc of a certain circle, and then you can define a radius of curvature for these 2 points. So here, this is UT vector, and this is UN vector. While here we have, this is UT, and this is UN. And we have the same idea for any position. Okay, here, for example, you have change of curvature, so UN will be downward. Okay. Now, how we define velocity and acceleration in this type of frame? First, for the velocity, it's very simple because already UT is defined as the unit vector of velocity. So vector V will always be along UT, and same sense and same direction. So vector V is magnitude of V times UT. And here in this frame, V is always positive. Why? Because UT will follow V. Okay? While in Cartesian, in rectangular components, ijk are fixed, so we can have positive velocities or negative velocities. Here, no. The V is always positive because UT will follow it. So UT will change in sense when V will change in sense. Therefore, if we define a curvilinear coordinate S, as we did last time, so S is function of time, then the velocity is simply given by ds over dt. And it's always directed along ut, which is tangent to the path. Now, what about the acceleration? So for the acceleration in normal tangential coordinates, we have two components of acceleration. We have the tangential component and we have the normal component. If you are interested in the derivation of this formula, I can explain it for you anytime you want, but to not lose time now, I will just give you the main issues. But we can organize office hours, and I can explain it for you if you are interested. So you have two components of acceleration: tangential one, which is along ut, and normal acceleration, which is along un. Why we have a TAN? Because in order to do a curvilinear motion, I should have an acceleration component along un to be able to change in velocity direction. Okay? So if I don't have an, what will happen? I will go on a straight line. I cannot change velocity direction if I don't have normal acceleration. So by definition, AT is due to change in speed, and AT is defined as dv by dt. Okay, so here, as you can see in this relation, AT represents the derivative of velocity with respect to time. So if you have change in speed, you should have tangential acceleration. While if you have change in direction, then you should have normal acceleration. And the normal acceleration is defined by v square over rho, where rho represents the radius of curvature, okay, and v represents the velocity. So always, when you have a curved motion, it's possible to have AT0 in case no change in speed, but it's not possible to have AN0 as long as I am moving on a curve, because to change direction of velocity, I need an acceleration, which will be directed along the normal component. So in total, the total acceleration in curvilinear motion can be calculated as a radical of AT squared plus AN squared. Okay? And of course, since in curvilinear motion, AT is dv by dt, not the total acceleration, so pay attention for this. AT is dv by dt, not an, or not the total acceleration. So in case you have constant AT, you can apply all relations we developed together for constant acceleration. But if you have constant an, or if you have just constant total acceleration, you cannot apply these relations, because these relations are derived based on dv over dt is constant. And in curvilinear motion, dv by dt is at. Okay? Now, we have seen together that the normal acceleration an is given by v squared over rho. So in order to compute the normal acceleration, we need to know two informations at a certain point. We need to know the speed, and we need to know the radius of curvature. The easiest case will be a circle. So if you move on a circle, at any point, what is the radius of curvature? It's of course the radius of the circle. In a general case, if you have, for example, any curve, how to find the radius of curvature? We have a mathematical technique. If I give you the graph of a path and I give you y function of x, if you want to determine what is the value of rho in this case, okay, then you can use the following formula. Okay, so rho is equal to 1 plus dy over the x squared, the whole term to the power 3 over 2, over the absolute value of the second derivative. So this is a way to calculate rho in case I have the function y function of x. Okay, we will do practice on this in problems. Let us do this example. When the skier reaches the point A along the parabolic path, he has a speed of 6 meters per second, which is increasing at 2 meters per second squared. So look here, what do you think this acceleration is? Which acceleration? Normal, tangential, or total? When they tell you the speed is increasing at 2 meters per second squared, 2 meter per second square represent what? No, Stephen, not the total. I will tell you why. Yes, it's 80. Look, because by definition, what is 80? 80 is dv by dt, okay? So when we express the change in speed, increase or decrease in speed, then we mean the tangential acceleration, okay? Because the total acceleration here is divided into the tangential component, which account for change in speed, and the normal component, which account for change in direction, okay? So here, since they are saying that the speed is increasing at 2 meters per second square, this means that AT positive. Because as we have seen here, in normal tangential coordinates, V is always positive. So when I have acceleration, then AT is positive. And if I have deceleration, AT will be negative. So I can write that V at point A is plus 6, and A at A tangential. So the tangential component at A is plus 2. Now, they are asking me to determine the direction of his velocity and the direction and magnitude of his acceleration at this instant, and neglect the size of the skier in the calculation. So here, I want to find what is the direction of velocity and what is magnitude and direction of acceleration. I will open a new session to continue the problem, okay?